Hello students, this is Snitha Shetty, Assistant Professor, Department of CSC, AJT Mangalore. In today's session, we'll discuss about random variate generation. So this comes under Module 3. So in my previous session, I explained about the random number. So in Module 3, there are two chapters. One is random number generation and second one is random variate generation. So we already completed the first chapter, that is random number generation. Okay, so there we studied what is random number, what are the properties of random number, and different tests on the random numbers. Okay, so in here in this chapter we are studying random variate generation. Okay, so let's discuss what is random variate. Okay, what is the meaning of random variate? So the random variate, it is a value being sampled from a proven distribution of an input variable. Okay, so it is a value being sampled from a proven distribution of an input variable. So the general example for random variate is inter-arrival time or the service time. Okay, so which we take for example in the first module. So we have done a bank simulation, right? So there we assumed the inter-arrival of the customer or the service time of the customer. So all those values we call it as a random variate. Okay, so here the random variate, so it is a value, it is a digit. Okay, so it should satisfy all the distribution. Okay, now before that, so we studied the random number and what is the basic properties of the random number. The random number should satisfy two property, right? So which are those? They are uniformity property and independence property. So the random number should have two important properties. They are uniformity property and independence property. So we are conducting test, right? So the first case test and chi-square test, it will check uniformity property, and autocorrelation test will check the independence property. Okay, similarly here also the random variate, so it should satisfy some distribution. Okay, so here it is assumed that distribution isn't completely specified. Okay, so it should satisfy some of the distribution. Now what is the distribution? I'll be talking later. Okay, so before that, the random number, when we generate a random number, first it will generate an integer x, right? So for example, the first method, the linear congruential method. In linear congruential method, it will generate x. So it's like xi plus 1 is equal to ai x plus c mod m, right? X plus c mod m. So when you generate xi, you can generate ai. So for example, the formula was like this in linear congruential method. So first it was generating xi, right? First it was generating x value. So it was xi plus 1 is equal to axi plus c mod m, right? So first if I equal initial I will be 0. So first we used to generate what? We used to generate x1. So if we get x1, and from there directly we can obtain r1, right? So what's the formula to generate r1? R1 was R1 is equal to xi divided by m. So if you generate x2, you can generate R2. So if you generate x3, so here you can generate R3, right? So this was a random number. So in order to generate the random number, we need an integer. Okay, so this integer is known as random variate. Okay, so this integer is known as random variate. So here when you generate a random number, the random number should satisfy two important properties. They are uniformity property and independence property. So here also when you generate the random variate should satisfy some of the distribution, and those distribution are, it should satisfy exponential distribution, uniform distribution, Weibull distribution, Poisson distribution, and triangular distribution. Okay, so all the random variate should satisfy some of the distributions like exponential distribution, uniform distribution, Weibull distribution, Poisson distribution, and triangular distribution. Okay, now, so there are different techniques to generate a random variate. So similarly, there was different technique to generate a random numbers, right? So we studied linear congruential method, combined linear congruential method, or multiplicative linear congruential method. So those were the methods to generate a random number. So similarly, to generate a random variate, there are several methods. Out of that, in this chapter, we are studying two methods. They are inverse transform technique and acceptance rejection technique. Okay, so these are the two techniques to generate the random number variate. Okay, so inverse transform technique and acceptance rejection technique. So here, when you are generating the random number, the input should be the x1, x2, x. That means if you know x1, you can generate r1. If you know x2, you can generate r2. So if you know x3, you can generate r3, right? So similarly, now we are generating x1. So in order to generate x1, you should know r1, r2, r3. If you want to generate x1, x2, x3, the input should be r1, r2, r3. Okay, so the name, the inverse transform technique. Okay, so this is a reverse engineering. From r1 you are generating x1. So in the previous chapter, if you know x1, we used to generate r1, right? Similarly here, if you know r1, you can generate x1. If you know r2, you can generate x2. Okay, so now when the random number is taken as an input, so both all the random numbers should satisfy the uniformity property. Okay, so both the technique assumes that the random numbers are uniformly distributed and readily available. That means in order to generate the x1, that means to generate the random variate, so the random number must be available. So both the technique assume that random numbers are readily available by satisfying the uniformity property. Okay, so here let's study. In this session, I'll be just talking about the inverse transform technique. Okay, so what is inverse transform technique? The inverse transform technique can be used to sample from exponential, uniform, Weibull, triangular distribution and empirical distribution. Okay, so here it generates the random variate which will support exponential distribution, uniform distribution, Weibull distribution, triangular distribution and empirical distribution. Now why the name is inverse? Why inverse? Because in random number generation, we used to generate r1 by x1. We used to generate r2 by x2. So here it is reverse, right? Inverse. From r1 you are going to generate x1, from r2 you are going to generate x2. Okay, so the name is inverse transform technique. Okay, so let's begin with the first distribution, exponential distribution. Okay, so we are applying inverse transform technique to the exponential distribution. Now, so what is exponential distribution? So before that, you should know what is probability distribution function and what is cumulative distribution function. So PDF is also known as probability distribution function. Okay, probability distribution function. So another name for probability distribution function is probability density function. So it is known as probability distribution function, or probability density function. One more name is probability density function. So what is CDF? So CDF is cumulative distribution function. Cumulative distribution function. Okay, so cumulative distribution function. So in your lower classes you might have studied this. Okay, in a probability distribution function or probability density function and cumulative distribution function. So let me give a simple example. Okay, assume a dice. Okay, so there are 6 possible number in dice, right? 1, 2, 3, 4, 5, 6. So what is the probability of that dice? The probability of dice is 1 by 6. Okay, so the probability of dash is 1 by 6, right? So probability is 1 by 6. So what is cumulative distribution function? So cumulative distribution is, so probability of 1 is 1 by 6. Okay, so probability of second is 2 by 6. So probability of third is 3 by 6. So probability of 4 is 4 by 6. And probability of 5 is 5 by 6. Right? And probability of 6 is 6 by 6. So when you add all this, it is nothing but cumulative addition. Okay, so probability distribution. So what is the probability is out of 6 will get in 1 by 6. Okay, what is cumulative probability? When you add 1 by 6, 2 by 6, 3 by 6, 4 by 6, 5 by 6, 6 by 6, we call it as a cumulative distribution function. Okay, so in exponential distribution, in each distribution we are seeing what is this PDF and what is this CDF. Okay, so let's begin with exponential distribution. So in exponential distribution, it is PDF, probability density function, so which is indicated by small letter f of x, and cumulative distribution function is indicated by capital letter f of x. Okay, so PDF means, you can say, observe here, small letter f, so cumulative means capital letter f. So here PDF f of x is equal to lambda of e to the power minus lambda x. Okay, and here the function x should be greater than or equal to 0. Okay, so I'll repeat this. The PDF of exponential distribution is lambda into e to the power minus lambda x when x is greater than or equal to 0. If x is less than 0, then it is 0. That is a probability density function of exponential distribution. Okay, so why we need this? Now in the next concept we are going to generate the random variate using this. Okay, using exponential distribution. So to generate the random variate, you should know what is a PDF and what is the CDF of each distribution. Okay, so we studied just what you understood, what is PDF exponential distribution. So next we'll see what is the CDF exponential distribution. So CDF of exponential distribution is integration of minus infinity to the x f of t dt. So in general I can say f of x cumulative distribution is 1 minus e to the power of minus lambda x when x is greater than or equal to 0, or f of x is 0 when x is less than 0. Okay, no need to derive. So you need to write the direct formula. Okay, derivation is not there. Just write the final formula. So you should study this formula. So the PDF is f of x. Cumulative distribution function is capital letter F of x is 1 minus e to the power minus lambda x when x is greater than or equal to 0, and f of x is 0 if x is less than 0. Okay, so and what is A of xi? So E of xi is known as expected value is equal to 1 by lambda. So it is nothing but lambda is known as mean. Okay, so 1 by lambda together we call it as a mean interval time. Okay, so this is about the exponential distribution. So the exponential distribution, you studied PDF, now you understood what is CDF, and this is the expected value. This is not required for the formula, but you should know that lambda means mean. Okay, and you should know what is cumulative CDF. It is 1 minus e to the minus lambda x when x must be greater than or equal to 0. Okay, so let's see how to generate the random variate using exponential distribution in inverse transform technique. Okay, or the heading is steps for inverse transform technique for exponential distribution. So this is an algorithm. Okay, so first compute the CDF of designed random variable x. Okay, so you should know the CDF of which distribution we are seeing. We are seeing exponential distribution, right? So step 1, compute the CDF. Just go back to the slide, see what is CDF. CDF is 1 minus e to the power of lambda x when x is greater than or equal to 0. Okay, so the CDF is 1 minus e to the power minus lambda x when x is greater than 0. So step 1, okay, in the algorithm step 1 is write the CDF. Yes, CDF is f of x is equal to 1 minus e to the power minus lambda x and x is greater than 0. Okay, second, set the range. Okay, so how to set the range? Now what you should do is, so f of x must be equal to r. Okay, so this is a step. The CDF should assign it to random number r. Okay, so random number will be given in the question itself. Okay, so set f of x is equal to r on the range of x. Okay, so f of x is equal to r. Now what is f of x? F of x is equal to 1 minus e to the power minus lambda x, right? F of x means 1 minus e to the power minus lambda x. So what I'm doing is, I'm just writing 1 minus e to the power minus lambda x is equal to r. Okay, 1 minus e to the power lambda x is equal to r. So here x is a random variable, r is a random number. Okay, so x is a random variable, so r is a random number. Okay, and we should make sure that I already told this, random numbers must be uniformly distributed between 0 and 1. Okay, now step 3, just solve this, compute this. So when you compute 1 minus e to the power of lambda x is equal to r, what answer will get is, just look at here. So this part, 1 minus e to the power minus lambda x is equal to r. Okay, so I'll move, just shift this e power minus lambda x to the right side, so that we will get e to the power of minus lambda x is equal to 1 minus r. Okay, so 1 minus r. So now I can write this as minus lambda x is equal to ln of 1 minus r. Okay, this is a ln function. Okay, ln function. So minus lambda x is equal to ln 1 minus r. Okay, now since this is a random variate, okay, I told random variable. Random variable is nothing but random variate. Okay, one name is random variate. Okay, don't get confused. Random variable and random variate both are same. Okay, random number is different. Okay, so what is the main aim? Why I'm doing this? I want to generate a random variate using r. Okay, so I want the value for x. So now I can derive the formula x is equal to, I can move this to right hand side, so I can write as x is equal to minus 1 by lambda ln of 1 minus r. X is equal to minus 1 by lambda ln 1 minus r. Okay, this is a very important formula to generate the random variate using exponential distribution. Okay, so using this you can generate the random variate for exponential distribution. Okay, so step 4, so generate the uniform random number as needed. Okay, for example, if they give r1, R2 and R3, you can generate 3 random variate corresponding to x1, x2, x3. Okay, x1, x2, x3. See, now x is equal to minus 1 by lambda ln 1 minus r. So, if I know ri, so I can generate xi. So, xi is equal to minus 1 by lambda ln 1 minus ri. So, if you want to generate x1 here, you should substitute r1. If you want to generate x2 here, you should substitute r2. So, if you want to generate x3 here, you should substitute r3. Okay, so you can generate n number of random variate. Okay, so based on the this algorithm. Okay, so this is an inverse transform technique only for the exponential distribution. Now let's look at the problem. Okay, so the problem they give on the question, generate the exponential random variate. Generate the exponential random variate with the mean 1. Okay, with the mean 1 for the following random number. For the following random number, so the random number is 0.1306, 0.0422, 0.6597, 0.7965, 0.7696. So this is a random number. So just count the number of random numbers. How many random numbers they given? 1, 2, 3, 4, 5. So they given 5 random numbers. So you should generate 5 random variate. Okay, now let's follow the algorithm. So what is algorithm says? Step 1. Okay, write the CDF. So here in question they mentioned using generate the exponential random variate. That means this is exponential distribution. Okay, step 1, write the CDF. Yes, you know the CDF. CDF is f of x is equal to 1 minus e to the power. This is e to the power minus lambda x. Okay, so this should be 1 minus e to the power minus lambda x. So I'll write here 1 minus. So 1 minus e to the power minus lambda x, x is greater than 0. Okay, write the CDF. So 1 minus e to the power minus lambda x, x is greater than 0. Okay, what is step 2? So step 2 is set that cumulative distribution function f of x is equal to r. Okay, set f of x is equal to r. So here you can see here. So when you set f of x is equal to r, so what happens? 1 minus e to the power minus lambda x is equal to r. Right? So we are setting f of x is equal to r. 1 minus e to the power minus lambda is equal to r. Okay, and x should be greater than or equal to 0. Okay, yes, we want to generate the random variate. Okay, so that 1 minus e to the power minus lambda x is equal to r. Okay, so now what is step 3? Compute. So when you compute, already explained this step, right? So when you compute, you will get the formula for x. X is equal to minus 1 by lambda ln of 1 minus r. Okay, so this formula will get in step 3 according to the algorithm. So x is equal to minus 1 by lambda ln of 1 minus r. Correct? Okay, now step 4. So how many how many random numbers are there given? So based on that you can calculate. Okay, so before that, here in question they given lambda, right? So what is that lambda? So see here in the formula you want to generate x. So to generate x, the land function of 1 minus ri is given. What is this lambda? So lambda is nothing but mean. Okay, so lambda is nothing but mean. So what is mean they given? So mean with generate the random variate with mean 1, right? So mean is equal to 1. That means your lambda is 1. Okay, lambda is 1. Okay, now so let's begin. So we'll generate the random number, random variate when r1 is equal to 0.1306. Okay, so r1 is equal to 0.1306. So what is your formula says? The xi is equal to okay, so minus 1 by minus 1 divided by, so what is a lambda? Lambda is 1, right? So next ln of, so land function 1 minus, what is ri? What is your r1? R1 is 0.1306, right? So here I am generating what? Now I is equal to 1. Okay, so we will assume first random number is r1. So x is equal to 1. Okay, so when you compute this you will get x1. Okay, just simplify, just calculate the value. So he will get the answer as 0.39 something. So I'll take it as 0.14. Okay, or you might get 0.14 itself. In case you're getting 0.39 also, I'll consider as 0.14. Okay, so what is x2? So x2 is equal to, so again it is minus 1 divided by lambda. So ln of 1 minus, what is your r2? So r2 is 0.0422, right? So 0.0422. So what answer you will get is, so the answer will be 0.0431. Okay, 0.0431. So here you see, you can observe here when r1 is 0.1306, you'll get 0.14 something. So when r2 is 0.0422, you'll get the answer as 0.0431. Okay, so similarly when it is x3, so x3 is equal to again minus 1 divided by lambda. Lambda is 1. So next ln of, so 1 minus, what is your r3? 0.6597, right? So you can write as 0.6597. So what answer you will get is 1.078. 1.078. So next x4. So x4 is equal to minus 1 divided by lambda. Lambda is 1, right? So next ln of 1 minus, so what is it? R4? 0.7965. 0.7965. So you'll get the answer as 1.592. Okay, and finally x5 you can obtain using formula minus 1 divided by lambda. Lambda is 1. So ln of 1 minus 0. What is your r5? So you can see here 0.7696. Okay, so it is 0.7696. So that you will get the answer as 1.468. Okay, so for 5 random number you can generate 5 random variant. So just look at the table, fourth step, you'll get the answer. So you can see 5 random variant: 0.1400, 0.0431, 1.078, 1.592 and 1.468. Okay, so if they give 10 random numbers, similarly you can generate 10 random variant. So this is a way of generating random variant if the distribution is exponential. Okay, the formula based on the distribution you're writing the formula. So here the formula of generating x only for exponential distribution, this is a formula. Okay, now you can generate random variant other distribution, the formula it varies. Okay, so next we'll see the uniform. So uniform distribution, so the uniform distribution, Consider random variable x that is uniformly distributed on the interval. So they given the interval between a and b. Okay, a reasonable guess. So they're given x is equal to a plus b minus ar. Okay, let's see how we are getting x is equal to a plus b minus a into r. Okay, so to do this, first we should know what? We should know the CDF, right? CDF of the uniform distribution. Okay, so this is the given the PDF and CDF of uniform distribution. Okay, so the PDF of uniform, what is PDF? It is probability density function or probability distribution function. So the PDF of uniform distribution is 1 divided by b minus a. Okay, 1 divided by b minus a, where x should be greater than or equal to a but less than or equal to b. So 0 otherwise. So this is PDF of a uniform distribution. But we need CDF, right? So what is CDF? CDF is cumulative distribution function. So let's look at cumulative distribution function of uniform distribution. So there they given f of x is equal to 0 if x is less than a. Okay, see, the it should lie between a and b. The interval is a and b. So if the x is less than a, then f of x is equal to 0. If x lies between a and b, then f of x is equal to x minus a divided by b minus a. Okay, so if it lies between a and b, then f of x is equal to x minus a divided by b minus a. If x is greater than b, then f of x is equal to 1. Okay, so if x is greater than b, then f of x is equal to 1. Okay, so this is a CDF, cumulative distribution function. Okay, so now let's follow the step. Okay, so what is the first step? The first step is you should write the CDF, right? So CDF of cumulative distribution function. So what is a cumulative distribution for CDF? So f of x is equal to f of x is equal to x minus a divided by b minus a, right? X minus a divided by b minus a. So it's already here. So x minus a divided by b minus a. So the algorithm says first you should know what? The CDF, right? So we know that it is x minus a divided by b minus a. So what is the second step? So second step we should assign x minus a by b minus a equal to r. Right? So when I write x minus a, b minus a equal to r, so I'll get this way, right? X minus a divided by b minus a is equal to r. Okay. So now when you simplify this, so you want to generate the formula for x, right? So when you write x, when you simplify this, you'll get x is equal to a plus b minus a r. Okay. So it agrees the first formula. So x is equal to a plus b minus a is equal to a plus b minus a into r. Okay, so this is how we are generating the formula for random variate using uniform distribution. So here also same thing. So if they give R1, you can generate X1. So if they give R2, you can generate X2. If they give R3, you can generate X3. If they give Rn, you can generate Xn. Okay, so this is very simple. So this is about the uniform distribution. So let's look at one more distribution, third distribution, that is Weibull distribution. Your Weibull distribution says the cumulative distribution function. Okay, so first they're given a small letter f of x there. So this is a probability distribution function. So it is here it lies between the range alpha comma beta. Okay, the previous distribution, the interval was a comma b. Here the interval is alpha comma beta. So f of x is equal to beta divided by a to the power beta into x to the power beta minus 1 e to the power minus x by alpha to the power beta when x is greater than or equal to 0. Okay, otherwise it is 0. So this is a PDF probability distribution function. Okay, so but in order to generate the random variate, we need what? We need cumulative distribution function. So now let's look at the cumulative distribution function. So the cumulative distribution function is f of x is equal to 1 minus e to the power minus x by alpha into the power beta when x is greater than 0. So this is a predefined cumulative distribution function of Weibull. Okay, so it is f of x is equal to 1 minus e to the power minus x by alpha to the power beta. Next step 2, so what we should do, we need to assign f of x is equal to r. So when you assign f of x is equal to r, you will get 1 minus e to the power minus x by alpha to the power beta equal to r. Okay, so now directly you can compute this to get the formula for x. So when you compute this, you will get x is equal to alpha in bracket minus ln 1 minus r to the power 1 by beta. Okay, so here also when they give r1, you can generate x1. Okay, r2, x2. So when they give rn, you can generate xn. Okay, so remember this formula. So this is a formula to generate the random variate using Weibull distribution. And so we studied exponential distribution. So we studied uniform distribution and Weibull distribution. Now let's move to the next distribution. So that is triangular distribution. Okay, so what is a triangular distribution? So the triangular distribution says the PDF. Okay, so f of x is equal to, so if x lies between 0 and 1, so your PDF is x. Okay, so if x lies between 1 to 2, okay, so here the interval is from 0 to 2. Okay, remember the interval is 0 to 2. I can show you the graph. So triangular distribution is something like this. Okay, so you can see this graph. So density function for the particular triangular distribution. So here it ranges from 0 to 2. Okay, here one, this is height, so this is a height. Okay, so the interval of triangular distribution is 0 to 2. So based on that, they could generate the formula for PDF. So when x is between 0 to 1, okay, that means when x is between this value 0 to 1, this range, okay, 0 to 1, so what is PDF? PDF is x. Okay, when x is between 1 to 2, the PDF is 2 minus x. Okay, if x lies between 1 to 2, okay, so that means this range from 1 to 2. If it is between 1 to 2, okay, what is the PDF? 1 to 2 is PDF is 2 minus x. Otherwise, it is 0. Okay, so similarly, what is cumulative distribution function? So they are given the formula f of x. If x is less than 0, it is 0. Fine. If f of x, if x is less than 0, the CDF will be 0. Okay. If the x range from 0 to 1, okay, if x range from 0 to 1, so from here to here, what is CDF? So CDF is x square by 2. Okay, so if x between 0 to 1, CDF is x square by 2. Okay, now if x lies between 1 to 2, okay, that means this range. If x lies between 1 to 2, okay, so what is f of x? 1 minus 2 minus x whole square divided by 2. And if x is greater than 2, then f of x is 1. Okay, f of x is 1. So based on this, they given the value of what is if x is less than 0, if it is between 0 to 1, between 1 to 2 and greater than 2. Okay, so this is a triangular distribution they are given. Okay, so now see, in the previous distribution, there was only one formula, right, in CDF, but here they're given two values. So the CDF, here you can see two possible value for CDF. So one is x square by 2, one more is 1 minus 2 minus x square by 2. Okay, so in step 3 of algorithm, so you should compute r is equal to x square by 2 as well as r is equal to, r is equal to 1 minus 2 minus x square by 2. Okay, are you getting this? Since there is two formula, two CDF, x square by 2 and 1 minus 2 minus x square by 2. So r becomes x square by 2 and one more r is 1 minus 2 minus x square by 2. So you can see here 1 minus 2 minus x square by 2. Okay, so now when you compute that, when you simplify that equation, you will get x is equal to, since there was 2r, right, I mean two values, so you can the formula for x is two values. One is square root of 2r. Okay, one is square root of, when you compute this 2r, x becomes square root of 2r. Okay, x is equal to square root of 2r. So here the condition is the given random number should lie between 0 to 1 by 2. That means given random number should range between 0 to 0.5. If the random number is if it is greater than 0.5 to 1, then this formula applies. So x is equal to 2 minus square root of 2 1 minus r. See, the random number will range from 0 to 1, right? If the random number is greater than or equal to 0 but less than or equal to 0.5, then how to generate x? X is equal to square root of 2r. Okay, and if the given random number is greater than 0.5 but less than or equal to 1, how to generate? It is 2 minus square root of 2 into 1 minus r. Okay, so this is a formula of generating the random variate using triangular distribution. Okay, hope it is clear. So we studied four distribution. We studied first one exponential, then we studied uniform, then Weibull, then triangular. Okay, so here I have already told the input is given set of random number, right? So based on that we are generating random variate. Okay, now so when they give five random numbers, fine, you can generate five x values. So when they give more than 10, for example, if they give 15 or 20 random number is, you can generate 20 random variate. But what if the input is large set of sample data? It's very difficult to keep on generating x1, x2, x3, x4, right? So for that the solution is next step of distribution, that is empirical distribution. Okay, so here what if there is a large sample of data? When the sample of data is very less, we can follow any distribution, right? But what if the input is large? Okay, so when there is a 710 of thousands, okay, when there is more than 10 or more than 1000 sample of random number, it's very difficult to follow the previous distribution. Okay, so what we are doing is in empirical, okay, in empirical continuous distribution, okay, again there is two types, empirical continuous, empirical discrete. So here we are discussing only one type, that is empirical continuous. So in empirical continuous distribution, what we are doing is first summarize the data into frequency distribution with smaller number of intervals. Now what you should do is, now you should set that input, when there is a large number of input, divide that input into group of interval. Okay, group it into the some interval. I'll show you the example. So summarize the data into the frequency distribution with small number of interval. Okay, next afterwards fit continuous empirical distribution to the frequency distribution. Okay, so here we need to generate a formula using slope. So the formula of slope is ai is equal to xi minus x minus 1 divided by ci minus ci minus 1. Okay, and inverse CDF is given by x is equal to x minus 1 plus ai into r minus ci minus 1, when ci minus 1 is less than or equal to r, less than or equal to ci. Okay, see here, so this is a formula of slope. Okay, now we can generate the random variate x using this formula. The formula is, this is an interval, small letter x is an interval, xi minus 1. Okay, so here ai into r is a given random number. So c is a cumulative distribution function, and what is a is slope. Okay, and look at the range, this should be I minus 1, and this is Cm minus 1. Okay, so this you'll understand when you look at the problem. Okay, so let's look at the problem. So they given the data. Okay, so suppose that there is 100 machine repeat time have been collected. Okay, the data is summarized into in table 3 in terms of observation in various intervals. So there is 100 observation, 100 machine repeat, but that 100 they are divided into the intervals. Okay, so for example, there was 31 observation between 0 to zero point 0.5 hours. So total observation is how much? Total observation is 100. Okay, so first 31 is in this interval. In given question they given, okay, they have summarized the data. So they are telling, so there was a 31 observation in this interval, and there was 10 observation in this interval, and there was 25 observation in this interval, and there was 34 observation in this interval. Okay, so for example, there was 31 observation between 0 to zero point 0.5 hour, 10 between. Okay, so here in question they given, okay, so that is 31 observation between 0 to zero point 0.5 hour. Okay, 0 to 0.5 hour, and 10 between 0.5 to 1 hour, and so on. Suppose it is known that all the repeat takes at least 15 minutes, so x should be greater than or equal to 0.25. Okay, so minimum is 0.25, so instead of 0 we are starting from 0.25 here. Okay, so the 0.2, it should be minimum, there should be 15 minutes. Okay, so 0.25 to 0.5. Okay, so set x is equal to 0.25. Okay, so you don't get confused here. So even though they given that one from 0 to 0.5 hour, here next they given set x naught is equal to 0.25. Okay, so I'm taking 0.25 to 0.5. Okay, so next they given 0.5 to 1 until 2 hours. Okay, so next the frequency they're given, so this data is given in the question. Okay, next what is the relative frequency? So divided by 100. So when you divide, you will get 0.31, 0.10, 0.25, 0.34. Okay, so cumulative frequency means you are adding 0.31, 0.41. Okay, when you add this 0.3031, 0.10, 0.25, will get 0.66, right? So when you add 0.66 plus 0.34, you will get 1.0. Okay, so next calculate. So let's construct a graph here. Okay, later I'll explain how to generate the value for the slope. So let's construct a graph. So just look at the graph here. So here x-axis and y-axis. So the x-axis is the interval, so it is 0.5. Okay, divided 1.0, 1.5 up to maximum is 2.0, right? Maximum is 2.0. Okay, next, so we can see here here y-axis is cumulative probability 0 0.2, 0 0.4, 0 0.6, 0 0.8 and 1.0. Okay, let's plot the graph. Okay, so what is your x naught? So the x naught is 0 0.25, right? So initially they are given set x naught equal to 0 0.25. So here you can see here 0 0.25 comes somewhere here, right? So 0 0.25 comma 0. Okay, so initial cumulative frequency is 0. So 0 point here somewhere here, sorry, here somewhere here, so 0 0.25.0. Okay, so once again I'll repeat this. So x naught they given, set x naught equal to 0 0.25, so it comes somewhere here 0 0.25 comma 0. So what is your next x1? See, what is your next x1? X1 is 0.5. See, x naught is 0.25, x1 is 0.5, x2 is 1.0, x3 is 1.5, x4 is 2.0. Okay, so if I tell x0, it is 0.25, x1 0.5, x2 1.0, x3 1.5, x4 2.0. So now using that value interval and using cumulative frequency, we need to plot the graph. Okay, so initially 0.25 comma initial cumulative frequency is 0, so it is 0. So what is your next interval? It is 0.5. 0.5 comma what is your cumulative one? C1 0.31. Okay, next, what is the second interval? 1.0. What is the cumulative frequency? 0.41. So here 0.41. So what is next? So next is this value, so that is 1.5 comma, okay, 1.5 comma 0.66, and finally it is 2 point here, sorry, 2.0 comma 1.0. Okay, so now just join this line, join this dot. Okay, so this dot, so this is slope 1, so slope 2, slope 3. Okay, and this is slope 4. Okay, so you got the slope. Okay, now generate the value for the slope ai. Okay, so what is the formula for slope, generating slope? Ai says that xi minus x minus 1 divided by ci minus ci minus 1. Okay, so ai is equal to xi minus xi minus 1 divided by ci minus ci minus 1. Okay, so here I can write ai is equal to first one. Okay, so that means a1 is equal to, okay, so what is xi minus xi minus 1? See, this is your xi, right? So that is 0 0.50 minus 0 0.25 divided by, so what is ci? 0 0.31 minus 0. Okay, so when you calculate that, you will get the answer as 0.81. Okay, similarly you can generate slope too. Okay, so how to generate slope too? So this and this, right? So here xi is 1. So how to generate a2? So a2 is equal to, okay, so a2 equal to 1 minus 0.50 divided by, okay, 0.41 minus 0.31. 0.31. Okay, so you will get the answer as 5. Okay, so you'll get the answer as, so this answer is equal to 5.0. So you'll get the answer as 5.0. Okay, so similarly you can generate a3. Okay, so how to generate a3? So this is slope 1, this is slope 2, this is slope 3. So how to generate slope 3? So here xi, so xi is what? 1 minus 50, 1.50 minus 1.00, 1.00 divided by, okay, 1.00, so divided by uh, 0.66, 0.66 minus 0.41. Okay, so when you simplify, you will get the answer as 2.0. You will get the answer as 2. Okay, and finally a4 equal to, okay, so this is 1, slope 1, slope 2, slope 3 and slope 4. So slope 4, it is 2 minus 1.0, 2 minus 1.50 divided by 1.0 minus 0.66. So you will get the answer as 1.47. Okay, so this is how we are generating slope AI. Okay, hope it is clear. So this range is clear, right? So the input is 0.25. So the frequency they given, calculate the relative frequency divided by 100, that is total number of observation is 100. Calculate the cumulative frequency and calculate the slope using graph. Okay, so in the graph here, the x-axis I'm taken as an interval and y-axis I'm taken as a cumulative probability. Okay, then just plot the graph using the interval and make sure that the starting interval, since they're given 0.25, we are beginning from 0.25, and initially cumulative frequency is 0. Okay, because this is 0th interval. From here it starts from first interval. Okay, here first interval it is 0.31, so initially it is 0. Okay, once you plot the graph, so then generate the value for the slope AI. Okay, so now why we are doing this? When the input is more, right? So when the input is more, so for any random number, now you can generate the random variate using this graph. Okay, now how? So assume they given the random number is 0.83. Okay, a random number is 0.83. So now just look at the graph and see where that 0.83 locates. Okay, so where is the position of 0.83? See, 0.83 somewhere here, right? 0.83 is somewhere here. So it lies between 0.8 and 1.0, right? So R1 is 0.83. So where the range of 0.83 is between 0.66 and 1.0. Okay, so the range is fourth range, right? So the range is between 0.66 to 1.0. So now, sorry, 0.66 and 1.0 is not range, it is a cumulative function. Just look at here. So 0.83 comes here, right? So when I plot the 0.83 to the graph, you can look at the slope. So it comes to this slope, right? So this is slope 1, slope 2, slope 3 and slope 4, right? So that 0.83 points to this value, this slope. Now look at this slope, look at the cumulative function. So the cumulative function lies between 0.66 and 1.0, right? So 0.66 and 1.0. So what is the interval? See, this is 0th interval, first interval, second interval, third and fourth interval. So the 0.83 lies between third and fourth interval. Okay, third and fourth interval. And what is the cumulative function? So cumulative function is 0.66 and 1.0. So here you can see here, so cumulative function, why? Because this is third interval and this is fourth interval. So third cumulative function is 0.66 and fourth cumulative function is 1.00. Okay, now you know C3 and C4. Okay, you can generate the value of X. So what is the formula to generate the value of X? The formula is X is equal to xi minus 1 plus ai r minus ci minus 1. Okay, so I is what? I is the fourth interval, right? So I is the interval. So what is the interval here? So the interval is I equal to 4. Okay, why? Because so this is first, so this is second. Okay, this is first slope, second slope, third, first, second, third, and this is fourth slope. This is fourth slope. Okay, so I equal to 4. So x4 minus 1 you will get as x3 plus ai, so a4 ri, okay, r1, look at the formula here. So it is r, okay, r is given random number, minus ci minus 1, so it is c4 minus 1. So c4 minus 1 means it is c3. Are you getting this? So I'll repeat once again. I am taking I is equal to 4. Why I is equal to 4? Because this is first slope, so second slope, this is third slope, and this is fourth slope. Okay, so I is equal to 4. So I minus 1 is x3 plus ai is a4 r1 minus ci minus 1. So this is c3. So what is x3? Your x0 was 0.25. So x1, x2. What is x3? x3 is 1.5. 1.5 plus what is a4? a4 is 1.47. And what is given random number? 0.83 minus what is C3? C3 is 0.68. So when you simplify this, you will get the answer as 1.75. Okay, now cross verify your answer. So when you draw the graph, when you plot it from here to here, so it should come to the random variate 1.75. So the graphical answer and theoretical answer should be same. Okay, yes, you are getting here 1.75. So similarly here also it is 1.75. Okay, hope it is clear. Okay, so now let's look at the second random number. Okay, so second random number. So what is your R2? Assume the random number is 0.33. Okay, assume the random number is R2 is 0.33. Okay, so when it is R2 0.33, you should get X2 as 0.6. Okay, now let's start. We'll see whether we are getting 0.6 or not. Okay, how? So first see where that 0.33 comes. Okay, in graph. So 0.33 comes somewhere here, right? So 0.33 comes somewhere here. So you can see here I am plotted here. This is R. Okay, I marked R2 here. Okay, when that R2 comes in which slope? A2. Okay, it comes in slope 2. So this is first slope, second slope, third slope, and fourth slope. Okay, so this R2 lies in this slope. Okay, now what is the interval? The range is what? 0.411, so 0.41 and 0.31. Okay, so 0.41 and 0.31. Okay, so what I equal to what? I equal to 2. Okay, so here I equal to 2. Why? Because this is second slope, first and second slope. So I equal to 2. Okay, and what is C2 here? Cumulative C2 is how much? 0.41, right? 0.41. And what is C1? C1 is equal to, so 0.31. 0.31. Getting? Okay, so now we'll calculate the formula. We'll calculate the value of x2. Okay, what is the x2 says? X2 is equal to xi minus 1. Okay, I is 2, right? So xi minus 1 is what? X1. Okay, x1 plus, so next is what? Ai. So what is ai? Ai is 2, right? Ai is 2. So next what? R, the given random number R minus Ci minus 1. So C2 minus 1 is how much? C1. So what is your C1? C1. Okay, C1. Okay, so now I'll substitute the value. So what is your X1? X1 is 0.5, right? So plus what is A2? A2 is 5.0, right? So 5.05. Okay, next R. So what is the given number R? R is 0.33. So minus, when you do C1, what is your C1? C1 is 0.31. 0.31. Okay, so just compute that. Okay, so you will get the answer as 0.6, right? So when you compute 0.5 plus 5 into 0.33 minus 0.1, you will get the answer as 0.6, right? So you can see here, you can cross verify the answer. So 0.5, when it comes here, you can see here, you'll get the answer as 0.6. Okay, so whenever if they give any number of random numbers, you can generate x1 based on this graph. Okay, so the previous distribution was, there was a separate formula for x1 based on the r1 used to generate x1. Okay, but here since it is graph, so directly no need to do it theoretically. So directly by looking at the graph, you can generate. See for r2, so directly you can plot here instead of doing it theoretically. So you can say this is x2, right? So if it is 0.7 something, so 0.7 comes here somewhere here, right? So it lies between somewhere here 1.5. So this is how we are generating the random variate when there is large number of random number. Okay, so the empirical distribution is mainly when there is more number of random numbers. Okay, so we completed empirical continuous distribution. So today we studied, I'll just give the summary of today's session. Okay, so we studied about the random variate and explained, I told what is the meaning of random variate, and one of the examples is interarrival time, or it can be a service time. Okay, and I told the random variate, so when you generate the random number, it should satisfy the property, right? Independence property and uniformity property. Similarly, the random variate, it should satisfy different distribution. So different distributions are exponential distribution, uniform distribution, Weibull distribution, Poisson distribution, and triangular distribution. So we have seen today's session, we've seen exponential distribution, uniform distribution, Weibull distribution, Poisson triangular distribution. So in my next session, I'll be talking about the Poisson distribution. I'll be solving more problems, okay, related to the different distribution. Okay, and here we studied the first technique. We covered inverse transform technique. Okay, so here the inverse transform technique we studied for 5 types of distributions. Okay, so next session we'll see what is acceptance rejection technique. Okay, and we'll see what are the distribution which supports acceptance rejection technique. Okay, so we Poisson distribution, mainly the acceptance rejection technique will support the Poisson distribution. And here I told what is the meaning of inverse transform technique. Okay, because why? Because since they're giving random number, so based on the using random numbers, we are generating the random variate. So the name is inverse transform technique. Okay, so next is about the exponential distribution. So we have solved one problem of exponential distribution. So here first we should know the PDF and CDF of various distribution. Mainly we should know the CDF of all the distribution. Okay, so here the CDF was 1 minus e to the power minus lambda x. Okay, 1 minus e to the power minus lambda x. So based on that, in step 3 we did 1 minus e to the power minus lambda x equal to r. Okay, then we generate the value for x. Okay, so next we saw the problems. So they had given the different random numbers. So based on the random numbers, we generated x1. So here they had given 5 random numbers. So we see we generated 5 random variate, right? So the uniform distribution. So next session we'll discuss a problem related to the uniform distribution. Okay, so here how we got the formula for x. So based on the CDF. Okay, so there was x minus a and b minus a. So next that is Weibull distribution we discussed. So Weibull distribution, it is mainly for the time, the Weibull distribution is introduced as a model for the time to failure of machine or electronic components. Okay, so here the range is between the alpha and beta, and make sure that your alpha must be greater than 0 and beta must be greater than 0. Okay, and one more thing here, the alpha is known as scale parameter and beta is known as shape parameter. Okay, alpha is known as scale parameter and shape is known as a beta is known as a shape parameter. Okay, so here first the CDF, what we are doing is f of x is equal to 1 minus e to the power minus x by alpha to the power beta. Okay, next we are setting f of x is equal to 1 minus e to the power minus x by alpha into the power beta. Okay, then we are solving x in terms of r else. So we'll get the formula of x. Okay, so next we discussed about the we discussed about the triangular distribution. So the triangular distribution is, again, it is a very important concept. Okay, in this next class we'll see a next session we'll see a problem. So the triangular distribution, so here we are getting two CDF. One is x square by 2. Okay, so x square by 2 when x is between 0 and 1, and one is 1 minus 2 minus x square divided by 2, that means x is between 1 and 2. Okay, so for this we are getting two random number. Okay, why? Because so r is equal to x square by 2, one more r is equal to 1 minus 2 minus x whole square divided by 2. Okay, and we can look at the graph here. Just look at the graph. So here we will get two formula. X is equal to square root of 2r, and one more is 2 minus square root of 2 1 minus r. Okay, and remember, when the given random number lies between 0 and 0.5, your x is always square root of 2r. Okay, just look at the value of random number, then you apply the formula. If the given random number is between 0.5 and 1, your x value will be 2 minus square root of 2 into 1 minus r. Okay, so this is about the triangular distribution. Okay, and next we discussed about the last one, that is empirical distribution. So you should know why the empirical distribution is required, and here we discussed about the empirical continuous distribution. Okay, so why this is required? Well, when there is a large sample of data. Okay, when there is a large sample of data, we are going for empirical distribution, because for each random number we cannot keep on calculating x1. So what we are doing is, based on the given input, we are classifying the input into the different intervals. Okay, we are classifying the input into the different intervals, then we'll plot the graph. So now based on that graph we can generate the random variate. No need to do it theoretically. Okay, so directly by looking at the graph we can generate the random variate. Okay, so here directly see here r1 is 0.83, directly we got 1.75, and r2 is we got 0.6. Okay, so just here I just cross verified, we are getting the same answer. So this is about the empirical distribution. So we'll study more in the next session. Thank you.